So what we do, we have in the first work a task to find the literature data and to choose the airfoil and to calculate some properties. Not all the properties you can find in the literature. For example, in many cases, what we see is the behavior of the lift and the drag coefficient, momentum coefficient, with respect to the angle of attack. Here we have alpha, let's suppose, and we have the coefficients. Let's say let it be drag coefficient CD, for example, and it's something behavior similar to the following. Okay, this is our CD coefficient for various values of the angle of attack. It's an experimental data. The curve is built by the experimental points. This is what we can find in the literature. Just the drag coefficient is not enough to calculate other aerodynamic coefficients. You will probably need to find other data like the lift coefficient. And the lift coefficient would also be found probably in the similar or same angles of attack, depend on the source where you find. Maybe would be similar or same values of the angles of attack, or would be different, no matter. But you have this data. Okay, you also may have a momentum coefficient, for example. Momentum coefficient is a bit different story. Okay, very small values, something like this, momentum coefficient. Cm. This is our Cl, for example, and this is CD. Big one or small one. Small one is for two-dimensional body, and the capital letter CD is for three-dimensional body. CD, Cl, Cm. This is the data which we usually obtain from the literature. So this is why I said take data from the literature. But not only these parameters you need to calculate inside your task one. You also will need to see what is Cn, normal force coefficient, and for example, the Ca, axial force coefficient. And the Cn and Ca you can obtain by two different methods. First, you can calculate by formula from the book. I can just give you the number of the formula, 118, 119. Okay, would be better even. 118 from the book and 119 from the book. So you can or calculate them by formula 118, 119, or you can take it from the literature, is the second option. So this is why I say if you are calculating by formula 118 and 119 or similar formula, you must compare with the available bibliographic data, because not all the coefficients you can find in the literature. Some of them you can just calculate using formulas from aerodynamics. And then if you receive from another source, you can do this comparison just to have an idea if you calculate correctly or not these coefficients. Because anyhow, you need to present CD, Cl, Cm, Cn, Ca, all this data you need to present. If you calculate some of them, you need to try to get reference from the literature. This was the answer on your first question. No, you work with the constant slope of the lift coefficient. We are not working in aerodynamics with the angles higher than the maximum possible or so-called stall angle of attack. Okay, you do not need to explain what happens here in this region because we are not working with flow separation. Actually, the modeling of the flow separation is outside of the first part of aerodynamics, which we study now. And I'm not asking you to study or to simulate this this question. You study and simulate only until you flow separation. Okay, this is the point of the flow separation here. So significant flow separation in the point of maximum lift coefficient. The second part of your question was, you do not see from what you're supposed to start in the work one, right? We use airfoil as a small wing, or we use the area of the airplane, how we have to start, how we must connect the wing and the airplane inside work one. I would like to explain you better what is the idea. Our idea in work one is to start to understand how the aerodynamic coefficient works, how the properties of the flight could be obtained from the aerodynamic coefficients. And for this reason, you must make a choice. For example, what kind of airfoil you like, I mean, which is better for you. From the experimental point of view, for example, you found really nice data which you can use in your work one. Or from another point of view, you found a nice airplane which is flying in incompressible flow, low velocity flow, and you would like to study this airplane. You know what airfoil is used on this airplane, and you have an experimental data about this airfoil. This is the wing of the airplane, and here is sort of the airplane. So this airplane you found, it has the wings, it has its weight properties, etc. So probably you know at which altitude it flies, right? And if you know at which altitude it flies, you will know with which density it flies. On the ground level, we know the density is the standard density. On some altitude, the density is changing, density is decreasing. So to know the density, you just need to go to the end of the Anderson book and you will see standard atmosphere table from where you can find relation between your altitude of the flight and the density. Also, probably you need to know the weight of your airplane. And not just one weight, probably you need the weight of the airplane with the fuel and the empty airplane or half empty airplane, because when airplane starts to fly, takes off, it's full, right? And when it flies on some high altitude, it's already not completely full of fuel. It loses some part of mass to reach the high altitude. So we need to know which is the weight of the airplane on ground and on its cruise flight conditions. Also, this airplane probably will have the size. I will show you the length of the wing, right? This wing also has some chord, size C. So when we know the length of the wing, we know the chord size, we can calculate the planar area, which is composed of two wings. So the area I will write here is 2 multiplied by the L and multiplied by your chord. You know the weight, you know the plane area. And then we start to play with the aerodynamic coefficients. We know, for example, the lift coefficient, which is lift divided by Q infinite S for our body. And L is the lift force, which is moving our airplane up. And the opposite force we have is the weight force. And lift force is equal to the weight force in case when we are taking off and in case when we have a cruise flight. So to determine the velocity of the flight, you need to have a lift equal to the weight. And it will be the simplest case. So we can rewrite our equation of the lift coefficient by the weight divided by Q infinite S, where weight is changing, right? On the ground is one weight. on the cruise flight is a different weight, and S is the area, which we just calculated, is constant value, and the Q is the dynamic pressure, which is calculated in the following way. I just to remember you, it's very well known. Density velocity in square divided by 2, where we have density of the flight. It can be flight on the ground level when we are taking off, or can be at high altitude flight when we have cruise flight. And velocity is the velocity of the flight, could be velocity of takeoff and velocity of cruise at any moment. So once we substitute the definition of the dynamic pressure, we will obtain something like this. Here would be the multiplied by 2, right? And would be density velocity in square multiplied by the area. And this is our CL. From here, we just can calculate the velocity. Just express velocity from this relation. And I will make it here. Velocity from this relation would be equal to, since it's in square here, would be the square root to weight divided by CL, then would be the density and the area. I think it's correct. And now we look back to our graphics of the lift coefficient. Okay, this is CL, this is alpha. And the graphics of the lift coefficient is something like this. We have two characteristic points here. This is zero angle of attack. So this point here, this point here on zero angle of attack is called CL alpha 0. And this characterizes this lift coefficient characterizes the cruise flight of our airplane. And we have maximum, CL maximum, which is characterizing for us the stall conditions or taking off the airplane. For this point, we will have the maximum possible velocity, V maximum possible, because for this case, our lift coefficient has its minimal value. I'm not considering negative angle of attack, because if we have practically no lift, airplane cannot maintain its horizontal flight, it will go down. So most pragmatic is to keep the angle of attack close to 0. So we have small but positive coefficient of the lift. And this maximum velocity would be calculated as to weight. Again, this weight is at high altitude, at some altitude. So it's not the initial weight of the airplane. We already lost some amount of fuel to get to high altitude. And divided by this CL alpha 0 and the density and the area. I will just move our alpha to a bit lower position. Okay, and the square root. Okay, this density here is also on high altitude. And then CL maximum we use to calculate the velocity of the stall condition. So it's the minimal flight velocity. I will write here stall, and here altitude equal to 0, and then here altitude equal to 0. And instead of CL, probably CL maximum. CL maximum. Okay. Since the CL maximum is high, we have a smaller stall velocity. Since here CL is low, we have high flight velocity. So this is what I wanted to explain you about relation between the airfoil and the airplane. Actually, to calculate the flight velocity of the airplane, you need to know several parameters like the lift coefficient. It should not be obligatory the lift coefficient of that airplane. You can select another airplane, airfoil, and use your airfoil data to calculate a new airplane, for example. But it must be the airplane with known area of the wing, and it must be known value of the weight of the airplane. And this can be taken really easily because for all airplanes you have this data. You have the data of the sizes, dimensions of any airplane, the weight of the airplane, and set. Actually, in future we will have a more detailed theory about the properties of the complete airplane, of the wing. We will see that there is another source of losses called the induced drag related to the trailing vortex. But this is very, very early to start talking about the wing theory. I'm just asking you, consider that we have this ideal case without losses on induced parameters, and calculate in this simple way as it's shown in the chapter 1 of the Anderson book. So our guideline is the first chapter of the Anderson book is basically all you need to know to calculate work 1 in the part of the stall or maximum velocity, and also in the part of conversion between aerodynamic coefficients. I would like to answer the question of Giovanni about lift to drag ratio. Lift to drag ratio is the aerodynamic criteria of perfectness of the aerodynamic body. So we take the lift force, which is created by the airplane or airfoil, and divide by the drag force created by the same airfoil. Dividing these two forces, we see how performant is our airfoil or aerodynamic body. And in the page 83, we have some example, right? We have an example that there is an airplane, very well made or designed airplane, and then an additional equipment is added to this airplane. Figure 158 is called the breakdown of various sources of drag on late 1930s airplane, Seversky XP-41. So the idea is the following. We have a completely fair condition along nose airplane, a perfect airplane, let's say a perfectly designed airplane. And this nice airplane, it has a CL coefficient equal to 0.15, okay? And it has initially the drag coefficient CD is equal to 0.0169. So lift to drag coefficient ratio here is a bit smaller than 10. A bit smaller than 10. Quite good lift to drag ratio. What does it mean? Let's assume it's 9 or approximately 9. What does it mean? That if lift to drag coefficient is 9, it means that we can have 9 times smaller drag or thrust of our engine to carry this air, to fly this airplane. For example, this airplane is 1 ton of weight. Weight is 1 ton, and so the thrust or impulsion in Portuguese, thrust of the engine should be 1/9 of ton. So basically 9 times smaller. So better is the lift to drag ratio, or bigger is the lift to drag ratio, more powerful should be the engine. So it will consume less fuel, it will probably work longer, can fly in longer distance. So better, bigger lift to drag ratio is better the airplane. Okay, but when you look to the picture 158, you will see that just the airplane by itself, it's not so operational. Probably you need to install an additional equipment there, like let's see, oil cooler, or you need intercooler, or you need the cockpit ventilator, or you need the antenna installed, right? If you do not install antenna on the airplane, probably you cannot communicate with Earth or with other airplanes. If you do not install intercooler, probably your energy performance would be not so great. If you do not have other like exhaust stacks, or you do not have some pieces of the airplane which are important for the flight, for communication, for the safety, this airplane will not be as good as it could. But installing every equipment, we are always increasing the drag of the airplane. For example, once we install the intercooler is a heat exchanger, okay, where you have you inject the air from one side and from another side inside the box. So there are channels here, air passes through the channels, and it cools down. Hot air from one side becomes colder from another side, exiting from another side. It's basically a heat exchanger, and then you increase the efficiency of the engine. So if you do not install this, you lose the performance of the engine. If you install, you have some losses of the flow because you have an additional drag coefficient on this device. Definitely, you have the drag coefficient because you have friction inside intercooler, and this, because of friction, you lose some part of energy. So you have a drag. This is one of the examples. Also, same thing for antenna. For example, if you install the antenna, it's a very small thing, but it will consume some part of energy as well, because antenna is like a cylindrical stick of some size, right? And around the antenna, the flow will behave in some turbulent way, and some drag also will be created because of presence of antenna. Not big, very small drag, but from one to another, you increase the drag coefficient. From one device installed to another device, you have bigger and bigger drag coefficient. So this means that following: if you design a perfect airplane, you have some very nice drag coefficient, like shown here. If you install an additional equipment, your drag coefficient will increase more and more and more, depending how much you disturb the external flow. For example, at the end here, we may see that it's the final drag coefficient is 0.0275. So it's basically 50% higher drag coefficient than initial drag coefficient because of additional equipment. So you decide if you need an additional equipment, which additional equipment you need, you install. But same time, you know that you need to pay, right? And the payment in our case is the drag. So you need to fly slower with this additional equipment. You will fly slower, or you need a more performant engine to fly. This is what Anderson is trying to explain, that for every decision, for every solution or technical solution, we must always pay. We pay by reduce of the performance, or we pay some other way. The last question of Giovanna was about the boundary layer. Let's see the airfoil. And I will probably exaggerate with the size of the boundary layer, because otherwise we cannot see anything. The boundary layer is very thin. It can be in order of 1% of size of the horde, for example. So if I try to paint here 1% of the horde, it will be basically the same line. So I will make the bigger boundary layer just to show you. And then boundary layer goes out from the airfoil. So this boundary layer is for us mathematically is what? Is a change of the velocity because of some friction process, friction of the flow with the wall, right? Because of the flow interacts or gas interacts with the wall. If we look from the mathematical point of view, we will see that the shear stress forces entering into the equations, they are probably equal to the viscosity coefficient, right? Multiplied by the velocity gradient. Velocity gradient. So we take from at any arbitrary point normal direction, and we will see that velocity profile. Okay, this is the velocity profile. Probably should. Inside the boundary layer, right here, we have the velocity changing. So we have the gradient of the velocity, some value, positive value, right? And outside of the boundary layer, velocity is not changing anymore with respect to the normal direction. So this du by dn for us inside the boundary layer has some value, and outside of the boundary layer it has no value. This is why inside the boundary layer we have shear stress, and outside of the boundary layer the shear stress would be equal to 0. And it's absolutely equivalent to the inviscid flow model. So if we do not have shear stress, we do not have the viscosity influence, and it does not enter numerically with equation into the equations of the flow, we consider flow inviscid. Even though if we use the viscous flow model or complete Navier-Stokes equations in the region outside of the boundary layer, shear stress is equal to 0. So all these forces and the works and energies of the viscous flow, they are equal to 0 basically. Okay. So this is why we consider outside of the boundary layer flow as inviscid fluid. And only inside the boundary layer, since we have the value of gradient, we consider viscous. No matter what is the type of the flow, it's a laminar flow or it's a turbulent flow, the formula is the same. For the laminar flow, we have the laminar viscosity is different, is small viscosity. For the turbulent flow, we have a much bigger turbulent viscosity, but the formula of the shear stress, it stays the same. So we consider for laminar and for turbulent flow the same idea. Viscous flow only inside the boundary layer region and non-viscous flow outside of the boundary layer region.